Good day, everyone. This is Mabel Mlalo from BSCES Section R, and I'm going to report to you the last three topic of Chapter 21. So let's begin with the pavement rehabilitation. There are a variety of methods can be used to rehabilitate pavements or to correct deficiencies in a given pavement section, including using overlays, sealing cracks, using seal coats, and repairing potholes. So, under pavement rehabilitation, there are three subtopics. The first one is the rehabilitation techniques and strategies. Rehabilitation techniques are classified into two. The first one is the corrective, which involves the permanent or temporary repair of deficiency on an as-needed basis, or preventive, which involves surface applications of either structural or non-structural improvements intended to keep the quality of the pavement above a predetermined level. Corrective maintenance is analogous to repairing a small hole in a cloth, whereas preventive maintenance can be thought of as sewing a large patch or replacing the lining in a suit. Just as with the sewing analogy, corrective measures can serve as prevention measures as well. To illustrate, sealing a crack is done to correct an existing problem, but it also prevents further deterioration that would occur if the crack were not repaired. A chip seal coat, which is a layer of gravel placed on a thin coating of asphalt, is often used to correct a skid problem but also helps prevent further pavement deterioration. This illustration illustrates a variety of pavement repair and rehabilitation alternatives and differentiates between preventive and corrective approaches. For example, preventive strategies for pavement surfaces include fog seal asphalt, rejuvenators, joint sealing, seal coats with aggregate, and a thin blanket. This figure is provided to assist understanding the purpose for which a given treatment is intended. The second subtopic is the alternatives for repair and rehabilitation. There are a variety of pavement rehabilitation techniques for both flexible and rigid pavements, and they may be corrective or preventive depending on the circumstances. For example, patching is always considered to be corrective and can be effective if properly done. Many patching materials are available. At the other extreme, overlays are both corrective and preventive and considered to be effective technique. Surface treatments can be either preventive or corrective and considered an effective means of maintaining roads on a regular basis. Lastly is the expert systems as tools to select maintenance and rehabilitation strategies. Expert systems, such as a branch of artificial intelligence, can be used in the selection of maintenance and rehabilitation strategies. Expert systems, or DES, are computer models that exhibit within a specific domain a degree of expertise in a problem solving that is comparable to that of a human being. The knowledge required to build the expert system is obtained by interviewing pavement engineers who have long experience and knowledge about pavement management. The, the acquired knowledge is stored in the expert system, which can be used to recommend appropriate maintenance or rehabilitation strategies. And since the information is stored in a computer knowledge base, diagnostic advice is available to those users who may not be as experienced. Now, let's move on to the next topic of Chapter 21, which is Pavement Rehabilitation Programming. In this section, we describe the process used to decide upon a specific program for rehabilitation. This requires decision about the type of repair or restoration technique that should be used for a given pavement section and about the timing or programming of the project. These decisions consider the design life of the pavement, the cost benefit of the project, and other physical and environmental conditions. AASHTO guidelines for pavement management systems analysis technique are divided into three main groups. The first one is the condition assessment, the second one is the priority assessment, and the third one is the optimization. Each method is used to determine the type of treatment and needed and the schedule for rehabilitation. Let's talk about the first one, which is the condition assessment. This method is used to develop single-year programs. The agency establishes criteria for the different measures of pavement condition against which comparison of the actual measurements can be made. If the measurement exceeds this limit or the trigger point, then a deficiency or need exists. Figure 21.18 illustrates this concept, or the concept of condition assessment, For example, if a limit of PSI of 2.5 has been set as the minimum acceptable roughness level for a particular class of pavement, then any section with a PSI less than 2.5 will represent a current deficiency. The fixed trigger point thus resolves the timing issue in a simple manner. Whenever the condition index falls below the given trigger point or the criteria, it is assumed that rehabilitation is needed. Therefore, by using the trigger criteria, all sections are separated into two groups, now needs and later needs. In this method, the concern is only with the now needs. Having decided upon the sections that need action, the next step is to select a treatment for each of these now needs. This could involve simple economic analysis methods such as the net present worth or the NPW or the benefit cost ratio BCR based on the approximate estimates of the expected life of the different alternatives. After deciding on the treatment, three possible situations may arise. The needs match the budget, the needs exceed the budget, or the needs are less than the budget. Of the three situations, The most common occurs when needs exceed the available funds, and so a ranking of these projects is often needed. The purpose of such ranking is to determine which needs could be preferred or deferred to the following year. There are several possible alternatives for ranking. Projects may be ranked by distress, a combination of distress and traffic, the net present worth, and the NPW, or the benefit cost ratio BRC. Sections are then selected until the budget is exhausted. The rational factorial ranking method, or the FRM, is an example of a ranking method, and it uses a priority index that combines climatic conditions, traffic, roughness, and distress. The priority index is expressed as y equals 5.4 minus the quantity of 0.0263 x sub 1 minus the quantity of 0.0132 x sub 2 minus the quantity of 0.4 log times x sub 3 plus the quantity of 0.749 x sub 4 plus the quantity of 1.66 x sub 5, where y here is the priority index ranging from 1 to 10, with the representing very poor and 10 representing excellent. Thus, a low value indicates a pavement has a high priority for treatment. And the x sub 1 here is the average rainfall. X sub 2 is the freeze and thaw. X sub 3 is the traffic. X sub 4 is the present serviceability index, and the X sub 5 is the distress, which is a subjective number between -1 and +1. To make it more understandable, let's have an example on determining the order of priority for rehabilitation. So we have here 3 sections of highway have been measured for surface condition with results as shown in table 21.9, which can be shown in the latter part of the report. Also shown are climatic and traffic conditions for its section. So we're going to use the rational factorial rating method to determine the order of priority for rehabilitation. Using the equation 21.10, we have here y equals to 5.4 minus the quantity of 0.0263 x sub 1 minus the quantity of 0.0132 x sub 2 minus the quantity of 0.4 log times x sub 3 plus 0.749 x sub 4 plus the quantity of 1.66 x sub 5. So the priority index, or the y for each section, is in section 1 we have y equals 5.4 minus, substituting all the values of x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. We have obtained the value of y in section 1 as 6.099. For the section 2, we obtain the value of y, or the priority index, as 4.998 And for the section 3, we obtained the value of y as 6.86. Since low index values indicate poor condition, section 2 should receive highest priority, followed by section 1, and lastly, the section 3. Now let's move on to the second subtopic of Pavement Rehabilitation Programming, which is the Priority Assessment Models. Priority assessment is used to develop multi-year programs, an extension of the single-year model described. It addresses the question of when the latter needs are to be addressed and what action is required. To use this method, performance prediction models are required. For developing multi-year programs using ranking methods, either fixed trigger point or variable trigger point methods are used. So, the trigger point ranking or models are used to predict when each road section will reach its trigger point. That is, instead of separating the network into two groups, present needs and later needs, this method separates the pavement section into, let's say, 6 groups according to the year where action will be needed, as illustrated earlier in the figure 21.19. The process from this point is essentially the same as the previous method, except that more accurate economic analysis is possible as a result of availability of prediction model. The use of a fixed trigger point method was illustrated in 21.4, in the example of 21.4. So this is the figure of the fixed trigger point ranking for pavement rehabilitation programming. And this is also the figure for the variable trigger point ranking method for pavement rehabilitation programming. Another one is the variable trigger point ranking. This also based on economic analysis models to establish the type of treatment as well as the timing. The advantage of using this method is that timing and treatment selection decisions are made simultaneously instead of being treated as two distinct stages in a sequential process, as was the case with the previous method. Next one is the near optimization methods. Near optimization methods are based on a heuristic approach which can yield good results in most cases. The marginal cost effectiveness method illustrates near optimization methods that have been widely applied. For this method, the cost effectiveness of various combination of highway system project sections, maintenance or rehabilitation strategies, and their timing are computed. So, effectiveness is estimated by computing the area under the condition prediction model between the curve and the established critical value for highway condition. So, effectiveness is calculated for a planning horizon, example 10 years, And areas above the critical value are positive, and those below the critical value are negative. The net area is multiplied by the section length and average annual daily traffic, or the AADT, and the result is a measure of the effectiveness of the maintenance or rehabilitation strategy being considered. So this figure illustrates the calculation procedure. The value of effectiveness is computed as the shaded area of the right of the rehabilitation strategy minus the shaded area to the left, then multiplied by the traffic volume and by the length of the transportation element. So we have here our formula in finding the effectiveness. The cost of the maintenance or the rehabilitation project includes the cost of materials and construction on an in-place quantity basis, such as dollar over mile. And user costs include delays and additional vehicle operating costs incurred during construction. Cost effectiveness of a given project is computed as effectiveness ratio equals to effectiveness divided by its cost. So the following steps are used to compute the marginal cost effectiveness. First step, for each highway section, select the combination of treatment alternative and year with the highest EC ratio, or the effectiveness cost ratio. Step 2 is compute the marginal cost effectiveness MCE of all other strategies including the combination of other treatments and other timings for each element, as MCE equals the quantity of E sub S minus E sub R divided by the quantity of C sub S minus C sub R, where E sub S is the effectiveness of the selected combination, E sub R is the effectiveness of the combination being compared, C sub S is the cost of the combination selected, and C sub R is the cost of the combination being compared. Step 3. If MCE is negative, or if E sub R is less than E sub S, then the comparative strategy is removed from the further consideration. If not, it replaces the selected combination. Then step 4, repeat the comparison process until the total cost of the selected projects utilize the funding available. Now let's have an example of the effectiveness of rehabilitation strategies. So we have here the traffic volume of a 2-mile pavement section is 10,000 vehicles per day. The deterioration relationship for sections in this family group is PQI equals to 10 minus 0.50 times the age, where PQI is the pavement quality index with values between 0 and 10, and the age is equals to the pavement age in years. The highway agency policy is to maintain pavement sections with a PQI which is less than 5. Resurfacing the pavement section will increase the PQI to a value of 9, And after resurfacing, the section is expected to deteriorate at a rate of 1.50 PQI points per year. Determine the effectiveness of resurfacing the pavement section after 12 years from construction, and what would the effectiveness be if the resurfacing is postponed until year 13. Another question is determine the time it would take for the resurfaced pavement to deteriorate to a PQI value of 5. So, this figure 21.22, illustrates the deterioration trend for the pavement section before and after the application of the rehabilitation strategy in year 12. The section condition deteriorates to a PQI value of 4.0 in year 12. After rehabilitation, the PQI value is restored to a value of 9, and the following rehabilitation, the deterioration rate is much faster than the deterioration rate of the original pavement structure and is governed by the following equation. So we have here also our solution. PQI equals 9 minus 1.50 times the age, which is the number of years after rehabilitation. So to determine when PQI will reach a value of 5.0 after rehabilitation, substitute 5.0 for PQI in equation 21.14 and solve for age after rehabilitation as follows. We have here 5.0 equals 9.0 minus 1.50 times the age after rehabilitation. Therefore, age after rehabilitation is equals to 2.667 years. Now let's compute the area in figure 21.2 to the right, which will be served as area 1, and to the left will be our area 2 of the rehabilitation strategy as follows. In computing the area, we have the formula here. Area 1 equals to 1/2 times 2.667 times 4.0. Then we obtain the area 1 as 5.334. For the area 2, we have 1/2 times 2.0 times 1.0. Then we obtain the value of area 2 as 1.0. Using the equation 21.11 to compute effectiveness, we have here the formula of effectiveness equals to area 1 minus area 2 multiplied by AA dt multiplied by its length of section. Then we obtain the value of effectiveness as 86,680. If resurfacing is postponed to year 13, the deterioration trend can be expressed as shown in figure 21.23. Note that the PQI will be 5.4 in approximately 2.67 years following resurfacing between years 15 and 16. In this case, the area calculations are as follows. Area 1 equals to 1/2 times 2.67 times 4.0 equals to 5.334. And for the area 2, we have here 1/2 times 3.0 times 1.5. Now we have a new value of area 2 as 2.25. Therefore, our effectiveness is equals to 61,680. Optimization techniques. Optimization models provide the capability for the simultaneous evaluation of an entire pavement network and as such represent another method for scheduling rehabilitation programs in which alternative strategies satisfy an object function subject to constraints. Optimization involves the following. Identify the decision variables and determine optimal values. 2. Formulate an objective function to be optimized. And 3. Establish the constraints of model. Let's talk about first the identifying decision variables. So decision variables reflect the selection regarding which pavement section must be maintained, the appropriate maintenance or rehabilitation strategy to select, and the year when maintenance work is required. The following set of binary variables with values of 1 or 0 are used to represent these decisions as follows. So we have here x sub ijt equals to 1 if section I is maintained using alternative j applied in year t, and then x sub ijt equals to 0 if section I is not maintained using alternative j applied in year t. The next one is to formulate an objective function. The objective function is the value to be maximized or minimized. For example, if the object is to use available resources effectively, the object function is stated in terms of maximizing the effectiveness of the work program. Effectiveness calculations, as explained earlier in example 21.8, can assume a variety of planning horizons. For example, calculating the effectiveness of different courses of action over the next 10 years. An objective function can be formulated as follows, where x sub ijt is the binary decision variable and bijt is the effectiveness of maintenance strategy, j for highway section I in year t, calculated using the appropriate production curve. Next is establish the constraints. Constraints are restrictions on the numerical value of a decision variable and reflect the limitations on available resources including money, time, personnel, and materials. One constraint that is inevitable is expenditures in a given year cannot exceed the available budget, which is formulated as follows, where d sub ijt is equals to the cost of maintenance j for highway section I in year t, and b sub t is the budget allocation in year t. An additional constraint is required to ensure that each section receives only one maintenance or rehabilitation strategy during the planning period, which is formulated as follows, where xijt are binary variables that assume a value of 0 or 1. In equation 21.15 through 21.17 can be combined to optimize the total present value of M highway improvement projects with K different maintenance strategies and a planning horizon of T years, which is formulated as follows. Now let's move on to the last topic of chapter 21, which is the GIS and pavement management. Geographic Information Systems, or the GIS, are a set of computer software, hardware, data, and personnel that store, manipulate, analyze, and present geographically reference or spatial data. GIS can link spatial information on maps such as roadway alignment with attribute or tabular data. For example, a GIS, a digital map of a road network, would be linked to an attribute table which stores pertinent information regarding each road section on the network. This information could include items such as the section ID number, length of section, number of lanes, condition of pavement surface, average daily traffic, and many more. By accessing a specific road segment, a complete array of relevant attribute data become available. This figure 21.24, illustrates one application of GIS in infrastructure management. The computer-generated map shows the major roads and is color-coded based upon the values of ride index. Ride index is a measure of pavement surface condition. An attribute table is provided for pertinent information related to a specified road segment. So, GIS includes procedures for 1. Data input, 2. Storing and retrieving data, 3. Data query, analysis and modeling, and 4. Data output. Data is accepted from a wide range of sources including maps, aerial photographs, satellite image, and surveys. GIS also includes a comprehensive relational database management system, or the DBMS, which uses georeferences as the primary means of indexing information. GIS also allows presentation of the data in a meaningful way, including map and textual or tabular reports. It provides spatial analysis and modeling procedures that perform computations on data groups or layers and identifies patterns and relationships. Due to spatial capabilities of GIS, including data storage, retrieval, analysis, and presentation of capabilities, the use of for pavement management system is increasing. Pavement management requires both spatial and attribute data. For example, location of pavement section, which is spatial or location type data, and the condition of those assets, which are attribute type data. Other pertinent information is required regarding each highway section, such as year of construction, condition history, and maintenance of history. So there are several advantages of GIS over other forms of data presentation and analysis. We have here the first one is the ability to overlay different layers of information. Road surface condition can be stored in one layer, pavement construction information in one another, and so forth. These different layers have a common coordinate system, allowing them to be overlaid in top of one another. The second one is the provision of intelligent maps, which access significant amounts of attribute data linked to the geographic features of the map. These intelligent maps can convey more information than may be immediately apparent. In addition, these maps can be managed, analyzed, queried, or presented in a more effective way than is possible with physical hard copy maps, such as by identifying all pavement sections below a specified value for a condition index. Advanced queries and data analysis are also possible. For example, to identify sections whose condition is below a certain threshold and at the same time are subjected to traffic volumes exceeding another threshold. The last advantage is use of topology to support decision making. Topology is a branch of mathematics which deals with the spatial relationships among features. It identifies that are within a certain distance from another feature or features totally within another features, including ones that are adjacent to one another, and so forth. These functions can be greatly support the decision-making capabilities of pavement management system for a wide range of applications, including the ability to coordinate the work schedules of different components or subsystems of the highway system. All in all, this chapter has described the procedures used to develop a pavement rehabilitation program. The specifics may vary from one state to another, but there is agreement on the need for a rational and objective process to ensure that funds are efficiently used for pavement improvements. The benefits of using pavement management systems are to improve performance monitoring, a rational basis for legislative support, determination of various funding consequences, improve administrative credibility, and engineering input in policy decisions. So, this ends the chapter 21 discussion. So, I hope you understand our report and thank you for listening. Have a nice day ahead.